Welcome to topic 2403. In our previous lecture, we explored the tools of ecological risk mapping. Now, we examine the application. We turn our focus to the Netherlands, a country that effectively invented modern water management. Specifically, we will analyze the Netherlands Climate Adaptation Atlas, de Klimaateffectatlas. This is not just a map, it is a national policy instrument that mandates every municipality to conduct a stress test for flooding, heat, and drought. We will dissect how this platform integrates satellite data, hydrological models, and AI to translate abstract climate risks into concrete zoning laws. Here is the roadmap for the session. First, we look at the national policy context, why the Netherlands treats climate adaptation as a core state function rather than an optional project. Then we zoom into the atlas, what data layers it provides, and what it does not provide. Next, we clarify a common confusion. Hazard maps are not the same thing as risk maps. Risk requires exposure and vulnerability, which is where local data and sometimes AI methods enter the picture. After that, we examine the blue label as a communication device and a policy lever. We then connect the atlas to the municipal climate stress test and the follow-on step that matters most, the risk dialogue, where priorities and responsibilities are negotiated. Finally, we close with critique, atlas versus digital twins, key lessons, and a mini assignment that makes you rehearse the workflow in a local context. By the end of this topic, you should be able to describe the end-to-end logic of a national climate risk information system. How climate scenarios feed hazard layers, how those layers are interpreted locally, and how they are translated into planning instruments. You should also be able to interpret the blue label critically. That means understanding what it indicates, what it hides, and why a simple label can create both useful urgency and serious harm if it is used carelessly. A third objective is practical. Apply the climate stress test idea to a neighborhood-scale case. Even without Dutch datasets, you can reproduce the reasoning with local GIS layers, remote sensing products, and clear assumptions. A fourth objective is governance-oriented. Understand the risk dialogue and why inclusive participation is not a nice-to-have, but a structural safeguard against biased or illegitimate decisions. Your evidence will be concrete. Maps, a short policy note, and a reflection on uncertainty and ethics. The Delta program is the backbone of Dutch adaptation policy. It treats long-term climate and water risk as a national planning problem with stable funding, yearly reporting, and institutional continuity. The key point is not the exact legal structure, but the design philosophy. Decisions must remain valid across decades, even as climate conditions change. This is why scenario planning is central. If a policy assumes a single future, it becomes fragile. The Dutch approach instead asks, what measures keep working across multiple plausible futures? In planning terms, this is robustness, rather than optimization. The Delta program also forces coordination across scales. National water strategy, regional water boards, and municipal land use planning have to connect. That is exactly where an atlas becomes valuable. It provides a shared reference frame so different actors can argue with the same baseline information instead of competing narratives. The climate scenarios used in Dutch risk mapping come from KNMI, the National Meteorological Institute. A crucial point. Scenarios are not predictions. They are structured descriptions of plausible futures, built from climate model ensembles and storylines, designed for decision support. Why does this matter? Because planning is a choice under uncertainty. If you design a drainage upgrade only for one rainfall expectation, you may underbuild or overbuild when reality diverges. Scenarios let you test sensitivity. How does risk change under different warming pathways or circulation patterns? The atlas connects scenario logic to practical layers: extreme rainfall intensity, heat stress indicators, drought-related subsidence risk, and sea level influences. It also separates time horizons, so you can compare near-term relevance, useful for current investments, with end-century signals, important for long-lived infrastructure. A good planning rule is simple. Prefer measures that perform acceptably across multiple scenarios, and document where you are making bet the city assumptions. The Klimaateffectatlas is produced by Climate Adaptation Services and acts as a national, common language for climate impacts. It offers open, standardized layers and explanatory narratives so users can understand what the maps mean and how they should be used. The atlas is organized around hazard families. For water, it includes flood depth estimates and pluvial waterlogging indicators. For heat, it includes heat stress and urban heat island patterns. For drought and soil, it offers indicators related to subsidence and foundation risks, topics that are especially relevant in parts of the Netherlands. A major strength is accessibility. Layers can be explored interactively, filtered by scenario context, and then exported to local GIS workflows. That export step is where municipalities and consultants bring in local exposure layers and planning constraints. A major limitation is also clear. The atlas does not know your local assets, your social vulnerabilities, your critical services, or your political priorities. It provides the hazard canvas, not the final risk picture. This slide is the most important conceptual correction in the whole topic. Many people see a hazard map and assume it is a risk map. But hazards describe physical conditions, water depth, temperature stress, drought indicators, without saying who or what is affected. Risk appears when hazards intersect with exposure and vulnerability. Exposure is what is in the place, people, buildings, infrastructure, economic activity. Vulnerability is how sensitive those exposed elements are, building type, capacity to respond, socio-economic resilience, redundancy of services, and so on. Two areas can have the same modeled flood depth but radically different risk. A park and a hospital do not carry the same consequences. A wealthy household and a precarious renter population do not recover at the same speed. So, when using the atlas, the professional move is to combine it with land use, critical infrastructure layers, and vulnerability proxies, and to write down what is missing. If you cannot defend your assumptions, you are not doing risk mapping, you are doing map decoration. The blue label is often used to make climate risk legible to non-technical audiences. Think of it as a translation device. It compresses complex layers into a recognizable signal that can be linked to planning debates, property decisions, or investment priorities. This is powerful because it creates urgency. A label can motivate adaptation spending and push climate risk into everyday decision-making. But it is also dangerous because labels can stigmatize places, create fear, or shift burdens onto people with the least ability to respond. The key question is, what exactly is being labeled? Is it hazard likelihood, expected losses, or a composite index? If the label mixes multiple components, the weighting choices become political choices. Also, if the label is applied without clear uncertainty communication, it can be mistaken for a deterministic forecast. So, treat labels as communication tools, not truth machines. When you use them, explain inputs, thresholds, uncertainty, and intended use. And always ask who benefits and who gets harmed by the simplification. Where does AI enter this Dutch workflow? Often in the step that converts multiple predictors into susceptibility or impact estimates. Hybrid AI approaches combine physics-based reasoning with data-driven models, or they combine different algorithms to improve performance and stability. For example, flood susceptibility mapping might blend terrain derivatives, land cover, soil indicators, and hydrological proxies, then use machine learning to classify areas by relative susceptibility. The model can be calibrated and validated using historical events or proxy data, depending on availability. Hybrid approaches are attractive because pure physics models can be computationally heavy or require parameters that are not known everywhere, while pure machine learning can be brittle and sensitive to training data bias. The planning lesson is not, use AI because it is modern. The lesson is, use AI when it improves decision quality under constraints. That means you must report validation, be transparent about feature choices, and avoid treating accuracy as the only criterion. Interpretability and fairness matter because the output will influence real-world decisions. The municipal climate stress test is where national layers become local accountability. The stress test asks municipalities to evaluate how their territory performs under extreme conditions: heavy rainfall, flooding, heat waves, drought, and sometimes compound events. A good stress test is not only a map. It is a workflow. Choose scenarios, select relevant hazards, Combine with local exposure layers. Identify vulnerable functions, housing, mobility, health, critical infrastructure, and then document where thresholds are exceeded. The stress test is also designed to be repeatable. That matters because adaptation is not a one-time project, it is a continuous planning cycle. You run a stress test, prioritize measures, implement, and then update your assumptions and retest. Notice the governance logic. By making stress testing a normal municipal practice, the Netherlands shifts adaptation from optional innovation into standard duty. That is a powerful institutional design that other countries often lack, even when the data exists. After the stress test, Dutch guidance emphasizes a risk dialogue. This is the moment where maps meet politics, values, and responsibility. The dialogue typically involves municipalities, regional water boards, emergency services, utilities, housing organizations, businesses, and citizen representatives. Why is this step essential? Because risk is not only technical. Priorities depend on values. Protect what, for whom, and when. Maps cannot choose those trade-offs. Stakeholders also control different levers: zoning, drainage infrastructure, building codes, emergency planning. So coordination is the difference between action and paralysis. The dialogue is also a fairness safeguard. If only technical experts interpret results, you risk missing lived vulnerabilities and creating measures that protect assets while neglecting people. Labels and hotspot maps can also stigmatize neighborhoods, so the dialogue must include an ethics check. How will findings be communicated and used? The output is typically an adaptation agenda that assigns owners, timelines, and funding pathways, and then embeds that agenda into formal planning instruments. At this point, it is useful to compare two paradigms. The atlas is a curated set of layers, accessible, interpretable, and designed for broad adoption. A digital twin is more ambitious, a dynamic, data-integrated model that can simulate interactions, update with sensors, and support what-if analysis in near real time. Digital twins can be valuable for operational management and high-resolution forecasting, especially in complex urban climates. But they also bring risks: high cost, opacity, vendor lock-in, and the temptation to treat the model as reality. The Atlas approach is more democratic, in the sense that many users can access and critique it. Digital twins can become elite tools controlled by a few actors, which can weaken transparency and accountability. So, the critique is not that one is good and the other is bad. The critique is about fit for purpose. For many planning decisions, a well-documented atlas layer plus a transparent stress test may outperform a complex twin that no one can audit. The smart move is to choose the simplest tool that still supports robust decisions. This slide highlights the multi-hazard nature of climate impacts. Flood depth and waterlogging are only part of the story. Heat stress can drive mortality, reduce labor productivity, and amplify energy demand. Drought and subsidence can damage infrastructure and buildings in ways that are slow but extremely costly. A professional analysis does not treat these layers separately. It looks for interactions. For example, permeable surfaces can reduce runoff and also cool the microclimate. Tree canopies reduce heat but can be stressed by drought, changing maintenance needs and survival rates. When analyzing layers, you should also check scale and resolution. National layers may be too coarse for street-level design decisions, but they can still identify priority zones where detailed local studies should be focused. Finally, interpret layers as indicators, not precise measurements. Communicate uncertainty, and avoid false precision. If the map suggests high heat stress, confirm with local measurements or higher resolution modeling before making microscale claims. This slide is about translating information into governance decisions while remaining intellectually honest about limitations. Policies love simplicity, clear classes, thresholds, and categories. Science loves nuance, uncertainty ranges, scenario dependencies, and context-specific validity. The risk is that policy takes a complex map product and turns it into a blunt instrument. For example, a high-risk designation might be used in a way that depresses property values or drives insurance decisions without adequate safeguards. The solution is not to avoid policy. It is to build policy literacy into the mapping workflow. That means setting clear, intended use statements, providing uncertainty communication, and defining responsible interpretation rules. In practice, this is where planning ethics and data governance meet. Who owns the model? Who maintains updates? Who can challenge results? How are grievances handled if a community feels harmed by a label? The Dutch system tries to address these issues through transparency and a structured dialogue step, but the tensions remain, and they should remain visible, not hidden. Now we get concrete. Climate risk information only matters if it changes what planners do. The translation typically happens through instruments, zoning overlays, building permit conditions, investment programming, and nature-based design standards. A flood hotspot layer can support a zoning overlay that requires minimum floor elevations, prohibits vulnerable uses, or mandates flood proofing. Heat layers can justify cooling corridors, shade targets, or limits on impervious surfaces. Subsidence and foundation risk layers can influence construction rules and maintenance budgets. In many cities, the most effective actions are boring but powerful drainage upgrades, retention areas, green roofs, permeable pavements, bioswales, and tree canopy programs. These are not flashy AI products, but they are measurable, enforceable, and cumulative. The key is to connect each layer to a decision lever. If a map cannot be linked to a policy tool, it becomes a dashboard ornament. If it can, it becomes a planning instrument, especially when it is revisited in a cycle and updated with new data. The Netherlands case shows a repeatable pattern. Scenario framing to accessible national layers to local stress testing to participatory risk dialogue to formal planning instruments. That chain is what makes the system effective. Two lessons stand out. First, accessibility and governance matter as much as technical sophistication. A transparent atlas used by many actors can outperform a complex model used by a few. Second, risk communication is never neutral. Labels and hotspot maps change behavior and can produce unintended harms. A third lesson is methodological. Always separate hazards from risk. If you do not combine hazards with exposure and vulnerability, you are not mapping risk, and you may mislead decision makers. Finally, remember that AI enhanced is not a quality stamp. The quality stamp is validation, transparency, and appropriate use. The best model is the one that improves decision quality under constraints and can be explained to the people who are affected by its outputs. This case study connects to multiple parts of the module. It complements topic 2402 by showing what happens after AI-generated layers exist. They must be interpreted, combined with local context, and translated into planning action. It also links to broader topics on digital twins by providing a grounded contrast between an atlas approach and a full twin approach. It reinforces remote sensing and GIS skills because the atlas is essentially a structured remote sensing-informed GIS product. Layers, metadata, scenario filters, and export workflows. It also connects to governance and ethics themes, participation, transparency, and the social effects of labels. Finally, it links to learning outcomes around advocacy and implementation. You are not being trained to admire maps. You're being trained to use evidence to argue for better decisions. The Dutch workflow is a strong example of how to institutionalize that evidence pipeline so it survives beyond individual projects and remains part of normal planning practice.